Rook f is sort of a fancy lowercase f. T is for tension. I used to use T as the symbol for it, but that actually runs into a problem because capital T is also used for period. And there is a formula near the end of the course where we need tension and period both in it. So instead of using capital T for tension now, and then later going, oh, well, we're going to change that. Tension, just F sub T. W is for weight, or generically, any gravitational force. I'm going to write that a little bit differently. Weight, and then general gravitational force. The symbol I use for weight is a lowercase w. I put the little serif there at the end that indicated sort of a lowercase w. Capital W is used later for work, and it's helpful not to be using capital W now. The general gravitational force would be F sub G. We will get into that in chapter 9. And N is for normal. The symbol I use for normal is the same symbol that was used in the physics textbook when I took physics in high school, and we don't use it for anything else. I use a capital Y for normal force. Now, some of you astute observers might have noticed I skipped O. One, I needed a vowel for F-town, but it stands for other. The symbol used is problem specific. I'll explain in just a moment how we differentiate other from, I mean, it's not just, I don't know what it is, so I'm going to throw it into other.
What is that for?
Here, problem specific. The questions up to here. All right. Friction, the requirement is desire for objects to slide if this table is perfectly level. There's no friction between this bottle and the table because there's no desire for this thing to move one way or the other. If I tilt it, this thing now wants to slide down the ramp, so now there's friction involved. The direction of the force with respect to friction is that they are anti-parallel. Well, they're always going to be anti-parallel, but they're side by side in opposite directions. When I get into the force diagrams, this will become clear. This is sort of a reference we're setting up for right now. And the direction of the force with respect to the objects, because forces require two objects. And so that's what I'm talking about, the objects. So direction of force with respect to objects, it is parallel. The friction is always parallel to surfaces of contact. And it is surfaces of contact because, again, there are two objects rubbing against each other.
says direction of force with objects.
WRT with respect to
Oh, with
objects.
respect to.
And over here it's WRT each other, so with respect to each other. All right, tension. The requirement for tension is a tight rope, chain, string. Basically, it's a pulling force. And since forces come in pairs, if I've got a force diagram, I got my two tensions there. Those tensions with respect to each other are always going to point towards each other. And again, you'll see this a little bit later today. And the direction with respect to the objects, it is parallel, they are parallel to the tight rope, chain, whatever you happen to be using. Questions up to here about at least what I've written, the handwriting? Other, the requirement for other is unknown source or don't care about source. And when I say don't care about the source, this is not your own personal preference in physics. This is, from a physics point of view, do we actually care? So if I had, in the problem where I had the box and I said a 5 Newton force was pushing on the box, it did not matter what the source of that 5 Newton force was. That's a case where other. That 5 Newton would be an other because I don't care what the source was. Matter of fact, we didn't even know what it is because I didn't tell you. The direction of it are always problem specific. I'll just abbreviate problem specific. Weight, the requirement for weight is a little bit different than the generalized. Generalized gravitational force requires two masses. There's a gravitational force between any two masses. Right now there's one between you and the floor, between you and the overhead projector, between you and pretty much anything else that you can see around here. Weight is a specific kind of gravitational force. It is, the requirement is one small, and I put small in quotation marks, one small mass near one huge mass. And I got three words in quotation marks there. Small, near, and huge. They are, I'm not going to quantify them too much, but that small mass is small in comparison to the huge one. An elephant would be a small mass because the Earth is so huge. If we're talking about the weight of the elephant on Earth. Near, obviously, if you're on the Earth, that is very near. If you are on the top of the Empire State Building, that's still considered near. If you consider the size of the Earth, being close to it, you've got a lot of range there. The direction of the force, it is always vertical. Well, actually, it defines up and down. They're always pointing towards each other. And the direction with respect to the objects is force points to center of mass of other object. So the gravitational force that is acting on me is pointing towards the center of the Earth. Likewise, there's a force pulling on the Earth up towards me, up towards my center of mass. We're being drawn towards each other. All right, questions up to here? I thought I heard it, like someone was about to ask. All right. Normal force requires contact between two objects, contact of two objects. If you have three objects, then you would just do each pair separately. Normal force always points away from the pair, always point away from each other. And the direction of the forces with respect to the objects. Well, any of you happen to know what normal means in math?
Is it 0?
No. Yeah, that would be really misleading if this were a zero force. Normal means perpendicular. So it is perpendicular, the shorthand notation for perpendicular. I'll write it out in case you're not as familiar with the symbol, perpendicular. And I'm hoping that's the last time I write that word out. Perpendicular to the surfaces of contact. I do recognize I've just thrown a lot of words at you. We're about to actually apply it in just a moment. But I'll at least want you to have a reference that you can look on. Any questions before I erase?
May I take a picture of it?
Pardon?
May I take a picture of it?
Absolutely. There's also a video where I've done this as well as recording the class, but I mean, you know, if you take a picture, you'll have much more immediacy to it. And Kimberly, right? Okay. So, and Lacey did not come in, right? Anyone still writing this stuff down? All right. Eventually I'll find my tripod and then I can move the camera back and I can use more of the board. But the lines are marking basically what's within frame. We are now about to enter the exciting world of force diagrams. That's right, you've heard about it in legend and in song.
Let's go.
And we are going to start out with the exciting, incredibly exciting box falling. That's right, you heard it. So first thing I do is I'm going to draw the picture of what's happening. Box. Ground. This is probably the simplest force diagram that we will ever do. Matter of fact, it will become, at some point, it'll just be understood. Now, whenever I'm doing a force diagram, let me write that up there, just force diagram. Very similar to what's known as a free body diagram. So if you're going into tutoring and they start talking about free body diagrams is just a slightly simpler drawing of what we're doing right here, but my engineering background basically doesn't like free body diagrams. I'll talk about what a free body diagram would look like after I've done the force diagram. All right, so first thing I do is I now draw my objects. Now in this case, the box is still falling. It's a rather trivial redrawing of it, but I'm just going to draw a box, and I'm going to draw the ground. This will make more sense when we get to box on ground. That's right, this little teaser, what's coming up. And now I'm going to figure out what forces are involved. And so I bring out my checklist, F-town. So we go down the list. So let's start out with friction. Are there any two objects that are rubbing against each other or want to slide? All right. Friction, done. Not there. Tension, is there any type, rope, chain, string, or something else? It's gone. Other, did I introduce any force into this problem with an unknown source? I was a little bit more hesitant on that one. I did hear no whispered. Again, other would have been, and a 5 Newton force was pushing on the box. Weight. Okay? Because there is a small object near a huge object, the ground. Weight is a pulling force. It pulls things together. So it is pulling down on the box. And put a little W right there. And it is pulling up on the earth. And I use the exact same symbol for both. If I'm being really picky, these two lines should be the exact same length, just opposite directions. So if you'll notice under the weight and gravitational force in the chart we had set up that the forces point towards each other. I have a pair of forces. They are acting in opposite directions. And they point towards each other. Questions there before we tackle normal force? All right, normal force. The requirement is I have two objects touching each other. Do I have two objects touching each other? There we go. We've done with the very first force diagram. Woo! Bet you can't wait till Thanksgiving. You've got the relatives around and being, doing force diagrams. Yeah. I don't think I should be bringing you food. You need to bring me food. All right, so here's what a free body diagram would look like. In a free body diagram, you basically take what you have here, except instead of drawing a square to represent the box, you put a dot to represent the box, and you actually have to label it. I prefer the more visual of it. It also makes a difference if you are dealing with a situation where something might be spinning. Then it makes a difference where the force is applied. At this level, we're not worrying about spinning, but instead of just representing everything by a dot and then later on going, all right, so now let's draw it in 2 dimensions. I'm just going to start out with 2 dimensions. So again, this is the free body diagram, and this is what I'll be doing, what I call the force diagram. Yes, Brittany.
Do we need to know that free body diagram?
The only reason I bring free body diagram up is, label that, is that if you were working with someone else or you're looking at another textbook and they mention free body diagrams, I just want you to go, wait a second, I know he mentioned it.
If you were to do this, which one would you prefer us to do? The dots or the drawing?
I prefer the drawings. All right, any questions before we do box on ground? So the first thing I do is I draw what's the physical situation there. Box on ground, as advertised. Now I'm going to draw my two objects separately so I have room to draw my arrows. Please don't cram them all together. I got a box and I have the ground. I am not claiming the box is in the air now. All I've done is I've drawn a box and I've drawn the ground. I'm giving myself space here so I can draw arrows. Then we go down the checklist again. Is there friction?
Yeah.
I got a yeah there? Why?
Well,
No, there's no friction.
All right, just so you know, when I'm drawing up here, if it looks like I've drawn it so it looks like I'm trying to be level, then it's level. I have never played the game of, oh, I can't believe you missed the fact that it was at a 1 degree angle. No, if it looks like it's supposed to be level, it's supposed to be level. And as always, if in doubt, just ask. All right, so no friction because there's no tilt. The box does not have any desire to slide one way or the other. Or, from the other point of view, the earth doesn't have any desire to slide one way or the other. Tension?
no.
Nope. Other? Weight? Okay, which way is weight acting on the box?
Down.
And on the earth? Again, forces come in pairs. The only time I would not draw a pair is if there isn't another, just because there's some other nebulous thing out there which I don't care about. And normal.
Yes.
Normal is the force that